Good afternoon. Good to see everybody back. Everybody's still awake after lunch, right? Okay, good. All right, I'd like to take just a minute to tell you a little bit about Silman before I dive into the presentation. We are a structural engineering firm headquartered in New York. We also have offices in DC and Boston. We're about 150 people right now, and we just celebrated our 50th anniversary last year. We are a generalist kind of firm. We do everything from tiny restaurant renovations up through big new museum projects. We do a lot of new construction. We do a lot of adaptive reuse. We do a lot of historic preservation. So those last two categories are why we're here today. So why are we talking about digital documentation? Why is it important for structural engineers? Well, as we've already heard today, contemporary documentation is one of the best sources that we can have for an existing building. And if we're really lucky, that existing documentation looks something like this. It's nice, it's clear, it's complete, it's legible. But far too often, it looks like that. In which case, we have to come up with alternate methods. Silman has actually been involved in these alternate methods for quite a long time. This is St. Thomas Church in New York City. And our work on this actually started back in 1998, a project to analyze the vaults, and we laser scanned it. Because as you might notice, it's a little tall. And they didn't really think they could get a tape measure up all the way across there. So after the laser scan, we were able to generate a SAP model that helped us analyze the work on the vaults and come up with the numbers that we needed for this project. I will not say that this was easy. So 20 years ago, the scanning technology was nowhere near what it is now. The digital modeling technology was nowhere near what it is now. It involved a lot of back and forth between our team and the scanning team, and I think we even had a third consultant who was actually helping to build the SAP model. So lots of round and round, but we did eventually get the results that we need. You might recognize this project. This is another one of our early forays into laser scanning. This is the Guggenheim Museum, also in New York. Back in 2005, they started a major renovation project, mainly focusing on the facade and the mechanical systems, and Silman's work centered around the facade. The big problem, as you can see from the diagram on the bottom, was that there were a lot of cracks in the sprayed concrete walls all the way around the building. It's a really unusual building, really unusual geometry, difficult to document with conventional methods. So again, we scanned it. The cracks we were able to determine, I wrote a list of all the reasons that there were cracks in these walls. Thin cross sections, poor detailing and implementation of rebar, including discontinuities in the rebar and other structural systems, weathering from being in New York, and inadequacies in the original structural design. So sorry, Frank, but there was a lot of work to do. So we combined laser scanning with non-destructive evaluation rate, GPR, to identify some of the locations of those discontinuities in the rebar. And we're eventually able to combine everything into another SAP model, the deformed shape of which you can see in the upper left-hand corner. That's representing the building under, I forget whether that condition is wind or weather or temperature, but we were able to evaluate the building for its response to wind conditions and to temperature conditions. Again, I will not say this was an easy process. 15 years ago, lots of back and forth, lots of reiteration, but eventually we were able to get the data we need. That was 10 years ago, though. We've made a lot of progress since then, and I'm going to turn it over to Nathan, who could tell you about some of the things that we're doing today.
Thanks, Kate. So in the past, if we had a project where laser scanning was being performed, often we as structural engineers were just getting the indeliverable, so the CAD drawings or the BIM model that resulted from the laser scan. In the present, we're pushing more and more to actually get the raw data, the point cloud. And as we've been doing that, really the story of the present is the utilization from a structural engineer's perspective of some of that raw data. This is one of our recent projects. This is the Richmond Old City Hall in Virginia. It's an 1894 structure, and it's actually across the street from the Virginia State Capitol. So we're going to look at this one real quick as one of the case studies we present to talk about the present uses of laser scanning for the field of structural engineering. This is a photo from inside Richmond Old City Hall. There's actually a 4-story atrium space in there. And early on in the project, the design team commissioned a laser scanner to go out there and develop a point cloud from the laser scan. And then actually the architect, who was Quinn Evans, put together a Revit model. But rather than just getting the Revit model, we did push to get the point cloud data. And you can see right here, this is actually the laser scan point cloud data from that same atrium space. One of the technologies that's commonly used today is you actually have a camera with that's a part of the laser scanner, and so you can associate an RGB value with each of those individual points to get you a colored point cloud. This is from the space that's above the atrium. There's actually a ley light and a skylight assembly. And early on in the project, it became evident that we weren't going to be able to get up into this space to take measurements of the trusses. This presented a bit of an issue, though, because we were replacing the entire skylight and ley light assembly, and we didn't know if the existing trusses were adequate for the increased loads that we were putting on them. In conversations with the owner and the rest of the design team, we decided it wasn't adequate just to carry a large contingency about potential reinforcement of these trusses. And so we needed to figure out an alternate means of evaluating the trusses and their adequacy for these increased loads. As you can see, this is the point cloud. Luckily, the laser scanning company did go up into the attic space and was able to capture these trusses, and we were able to take that laser scan data and cut sections essentially to give us a good understanding of the overall geometry of the trusses and the individual members. Now, I won't lie, I think we got pretty good measurements for the overall geometry, but when you're talking about the individual members, it was hit or miss. So for instance, the top chord of this truss, we can pretty confidently say it's a 10-inch deep channel section that's 2 inches wide, but this laser scan in particular wasn't accurate enough that we could tell you the thickness of the flange or the thickness of the web. And so there was still a little bit of guesswork that went into this, but we were able to develop an accurate enough structural model that we could run the numbers and really refine the amount of reinforcement that we called for without ever having laid hands on any of these trusses. So this is a view of the overall point cloud. A laser scan for us in the structural engineering profession is not just for looking at these inaccessible spaces, though. Our office is a couple hours from Richmond, and so it really supplemented our site time. And having an accurate and reliable 3D representation of the building through this point cloud, it's very valuable for us in the engineering profession. We can go through this and determine, do the walls line up? Do the columns line up? And if they don't, do we need to do some additional probes there to understand what's happening? Do we need to figure out if there is a transfer girder that we hadn't been accounting for in the past? We can go in and take fairly accurate measurements of how far that beam is spanning. And you know, when you get back from a site visit, there's always that one room where you forgot to take a photo. By having the point cloud data readily accessible, you can easily go into that model and get a good visual of what that room looks like. The second case study I want to talk about is a project that we're actually presently working on. It's the Corcoran Gallery of Art. This is in Washington, D.C., and the Corcoran dates back to portions of it date back to the late 1890s. This is actually right across the street from the White House, and it was recently purchased by GW, or George Washington University, and they're adaptively reusing it to support some classrooms and also exhibits for the National Gallery of Art. At the Corcoran, the laser scan was performed early in design, and this figure shows the site, and each of those dots represents an individual scan. The different colors on those dots correspond to different elevations at which the scan was taken, so the different floor levels. So at the Corcoran, rather than working with the entire laser scan merged together, that can often be a lot of data, and with some of our computers, it can work pretty slow. So we actually would go to the locations of the individual scans, and we're able to take pretty accurate measurements from those. This is one of the auditoriums there. You're able to see exactly what the laser scanner saw at that location. So the photo on the right, or actually the point cloud data on the right, we can go into that and figure out pretty accurately, without being on site, where can we hang these new loads from the trusses. This is from a boiler room on the left here, and we can, from the comfort of our office, really, this is only 5 minutes from our office, but still, there's not a need to go out to the site if we can measure how far those ducts are, and if we can fit in this new stair just with the point cloud data. So the Corcoran Gallery really challenged us to balance traditional methods of data collection with new methods. So the traditional methods would be things like probes, hand measurements, photography, and some of the more modern technologies would be NDE, non-destructive evaluation, and laser scanning. And I really think that this is best illustrated by our investigations into the floor systems at the Corcoran Gallery. They used an archaic system that's called a Metropolitan slab, and that's actually what this is a photo of during construction. So what is a Metropolitan slab? A Metropolitan slab is a floor system where steel beams are spaced at every few feet on center, and then there's actually a cinder concrete slab spanning between that has draped wires in it. So when we first got brought onto this project, we did some NDE, non-destructive evaluation, using ground penetrating radar, and that's actually what that image is on the left. You can almost think of it as like an x-ray of the floor to identify where the steel beams were, the spacings, and then also where the draped wires are. We wanted to be able to correlate what we were finding with the GPR with some selective probes, and so that's actually what that image is at the bottom right, is a view to basically confirm what we're finding with the GPR. So one of the benefits that we've been finding as structural engineers for laser scanning is illustrating the flatness of different building assemblies, such as walls and floors. This is a masonry wall at a historic building that we were working on in Virginia, and we could tell that the wall was bowing, but it was difficult to determine the true extent. I think in the past we would have taken a plumb bob out there and taken a lot of measurements to try to develop essentially a contour map of how far this wall was bowing. What we did in this case is we actually laser scanned that wall, and then we were able to cut sections through the point cloud data to get a far more accurate representation of how much that wall was bowing at the different elevations and different locations. It really helped us to identify the true deformation of the wall. This is good for us as structural engineers, one, because it provides us with a better analysis approach. Rather than having to make conservative assumptions that this wall is 2 inches out of plane over the whole height, we can really refine that analysis. And it also helps us to focus our repair efforts. If through the point cloud, we can identify a few hot spots where the wall is really bowing, we can focus our investigations and future repairs. So that was in the past, and actually more recently what we've been doing is actually developing contour maps. Similar idea though. We basically drape a surface over the top of the point cloud, and then we determine the distance away from a reference plane. So for a wall, this would be a vertical plane, and for a floor, a horizontal plane. And you can see how far that wall is out of plane from that reference. At floors, similar approach, you can determine how much the floor is sloping or how much that deflection is at midspan. It also provides a good visual for the client. In terms of the structural analysis, this is the Lowe Library at Columbia University. we did a laser scan of the dome there. And a laser scan is critical for us as structural engineers, especially when it forms the basis for a finite element model. You can see a finite element model on the right there. As we're translating between a point cloud and a numeric or a structural model, it requires a lot of filtering of the data. You're going from potentially millions of data points to hopefully a few hundred, maybe a few thousand. And so that does take a little bit of an effort. We basically have to create a regularly spaced grid that still communicates the geometry, but won't bog down our structural analytical programs. There's no way that we would be able to incorporate millions of data points. It would just crash the structural programs. This is actually from a different project, Iglesia San Jose in Puerto Rico. But the reason I bring this up is a laser scan is going to capture the exposed surfaces. So you might catch the underside and the top side of a dome. But really, when we're doing the structural modeling, we're interested in the centroid of that section. And so it's not this direct translation. We actually need to figure out where the centroid is. And finally, so we've talked about the present and what we're doing in the structural engineering world with laser scanning and point clouds. But what does the future hold? We're starting to see shape extraction already, but the idea is that you would have a point cloud, and the point cloud, through running it through software, would actually automatically be able to identify wide flange sections rather than having to go in and make those measurements yourself. Drones, again, this is something that's already happening, but mounting laser scanners to drones, I think that we'll see that continue to develop in the next few years. And then just the merging of non-destructive evaluation techniques such as ground penetrating radar and thermography and others with laser scanning. And so often we as structural engineers are interested in what's hidden. And so that's the end goal, is a way to basically communicate the hidden in 3 dimensions.
I want to wrap up today by talking about the other side of digital documentation. We've talked a lot so far about point clouds and NDE, but for most of us, the deliverable is still 2D plans or sections or details or elevations. Even when something like the HABs and the hair drawings, they have to be translated back into 2D. So for us, that typically means BIM. Typically means something like this. It's a beautiful looking model. Is it useful? You can't tell by looking at it. And you also can't tell without having the conversation whether what you're going to get is going to be useful. Just to make a quick point, I'm probably preaching to the choir, but a point cloud and a model are not the same thing. The skills that it takes to have a good, useful point cloud are very different from the skills that it takes to have a useful Revit model or a useful 3D AutoCAD model. Sometimes those can be done by the same firm. Sometimes maybe not a good idea. I'm sure we could trade war stories about having outsourced the development of these sorts of models. But make sure that if you're going to work with somebody who is doing these for you, have a conversation. Make sure that you've got the right team for the things that you want to accomplish. How can you determine those things? This is a phrase that we have found very useful recently as we start to develop RFPs for delegating this kind of model creation, which is that we are asking our consultants to respect the orthogonal design intent of the building. For us, that means walls are straight, floors are flat, columns are vertical, corners are 90 degrees. Sounds great, right? Except we know that in existing conditions, none of those things are true, which is why there's an asterisk. Because all the things are within reason. And even that gets an asterisk because who decides what is reasonable? That's a conversation that you have to have with your design team. How accurate do you need to be? At what point are you willing to accept that a corner might really be 89.5 degrees? I have to tell you, we had one building where the client said, we're going to absolutely obey the point cloud, or we're going to trace it exactly. No 2 walls in that building were parallel. It was a nightmare. However, if you hold everything to 90 degrees, you may find that your Revit model is off by 6 inches at one end of the building, and that may not be acceptable either. So I can't tell you which way to go, but it's a conversation that you need to have. Some questions to ask. Assuming that, how many people work with consultants to do scanning as opposed to doing it yourself? Not many. Everybody else doing your own scanning? Okay, good. All right, so if you are engaging a scanning consultant, ask them what point density, ask your team, have the conversation with the scanner, what point density is required? The denser you need your grid, the more setups will be required, the closer access to your walls. Maybe for some things you can get away with being set up farther back and scanning the whole wall. Do you need a color scan? You saw some of our color scans earlier today. We've seen some nice black and white ones earlier. RGB may add some cost to your project. It may add some time. It may add cost because they need to turn the lights on for you. If you're scanning an occupied space and you can afford to do it after dark with the lights off, you might save some time and get in and out of the building quicker. Are the spaces accessible? I'm not actually sure how they scanned that skylight at Richmond Old City Hall. It's possible they kind of like reached through the wall and held still. But if you have a tiny space that needs to be scanned, maybe there's a small scanner that can be used. But if you don't know ahead of time, you're going to incur an additional mobilization cost when they have to go back and get the right scanner. And are there elements that need to be moved prior to scanning? Is there something temporary in the space that you can get out of your way so that you don't have to deal with it in post-processing? Is there furniture in the room that you'd rather not scan? Are there cars parked next to the building that you could move? Are you going to scan the outside of your building in the winter? Maybe when there aren't any leaves on the trees. Demolition. If you're going to demo all the interior finishes, do you really want to do the scan before you've done that work? Maybe you can wait a couple months, let the demo happen, then go scan. The last question for your scanner is, does the cloud need to be geolocated? So does it need to be tied to a specific survey datum? We heard from the Fort Jefferson team how they've specifically set up their survey network because you needed to link things in. Maybe you're just going out to grab a facade and it doesn't really matter what its survey coordinates are. Something to ask, a conversation to have. Let's say that somebody else is doing the modeling based off of your point cloud. We mentioned existing documentation. If you have some, why not use it? Unless you know it's unreliable, but see what you've got. The more you can get about the design intent, the better off you are. Again, accuracy, assuming accuracy and completeness. What details are needed? Do you need to have a solid model of every coping stone and every cornice and every window molding? Or can you get away with generic elements? No right answers, just cost implications. If you can't see something, how are you going to identify it? An example might be a basement wall. We can scan the inside, can't scan the outside. What are you going to do with that? Maybe you got your GPR and you can figure out how thick it is, but are you going to tag it somehow to say this wall is an assumed size, or we know this side but not the other side? There are things that you can do with the kind of metadata and object parameters to identify those kind of elements. You can't avoid them, so you need to talk about how you're going to handle them. I mentioned demolition earlier, same thing goes for modeling. If it's going to be demolished, do you need to model it? Sometimes the answer might be yes, because you don't know if you're going to demolish it at the time you do the model. Or you might know that an entire wing is going to go away, and you can get away without actually putting the effort into creating the solid model. And the last one, are there structural analysis requirements for the model elements? This one's for us. Everything else applies to all disciplines, but the structural is for us. Do you need solid elements? Do you need shell elements? Do you need plates? Those are kind of different. Each of those have their own requirements. Easy to do by a team if they know what you want ahead of time. If you come back to them later and say, oh, by the way, I needed the midpoint of that wall, probably asking for a change order. And I wanted to close with one image, which is what happens if you maybe don't have that conversation about what you want out of the model or the scan. I call this my ghost in the machine. And what is a little difficult to tell in this image is he's actually up there about 8 times. Because every time you move the scan, I guess he couldn't get out of the way. And something like that is very difficult to take care of in post-processing. You got to go and like find all those little tiny points. But yeah, I think in future we would make a note, scanner operator to avoid being scanned. Thank you very much.